intent of it. So anyways, nonetheless, let's get started. Today we'll continue on with of course, please make sure you're keeping up with the reading. Um, we left off last time, we talked about this idea of algorithmic execution, and the framing example I gave is the website purchase model. And in algorithmic execution, you have a series of steps, and in this case, it's 5 steps, and each step takes some time, right? And in this case, let's say you're buying something on a website. You visit a page, right? That takes time. You type in www.amazon.com, you hit enter, a whole bunch of stuff happens. Take computer networking, you'll find out what happens. Um, and you get the web page. So then that takes some amount of time. And if you visit Amazon again and again and again and actually time it, it's going to take different amounts of time. So the amount of time it takes for the page to load, that can be described by exponential distribution, which we talked about before. And then you enter in a search query for some product item, okay? And that takes some amount of time. It's not a lot of time, but if you do it again and again and again and instrument that with a timer, it's going to be some stochastic amount of time that you can also describe by an exponential distribution. So then you enter in a search query. Let's say you're shopping for, like I was before, a marinade injector, right? So you use it to, looks like a big metal syringe, and you use it to put marinade on stuff before you put it in the oven to get the marinade inside of the turkey flesh or whatever. Um, anyways, so you enter in a search query that's going to take a different amount of time. You get a result set. So your search query, you hit enter, that goes to the database, and it looks up product items that match that description and come back with a result set. So that result set computation from the database, querying for items that match a certain description, that's going to take some amount of time, and that too is stochastic. And then after that, you get your result set, it's rendered on your screen, you select something. And so the time it takes you to scroll through the result set of matching product items on your website purchase interaction and then select is going to take some amount of time. So that is also stochastic. And then, of course, you finish up the process and you pay for the item. That's going to take some amount of time and is also stochastic. Now, of course, certainly when you're dealing with a multi-phase process, step 1 through step 5, it doesn't have to be 5 steps, could be 20 steps, could be 100 steps, could be a small number of steps like 1 or 2 steps. But nonetheless, each step takes some amount of time, and that time is stochastic. And so, people, businesses, vendors, other folks are interested in analyses of these types of systems. For example, in a subway, right, there are certain processes involved. They greet you, take your order, ask you what kind of bread you want, and then ask you what you want in the sandwich. And then they ask you if you want it toasted or not. It either gets toasted or it doesn't. That takes some time. And then the other person puts on the finishing fixings on it for the sandwich. Now, of course, if you're dealing with a subway in a very busy area, let's say in the middle of a business district or what have you, you're very concerned about the total time that this process takes, even though each step itself is stochastic, because that time is called the service rate, right? And in operations research, you're concerned about the service rate that it takes to get a customer from the beginning of a process to the end of a process. You also have this idea of service rates when it comes to bathroom design, right? And when you design bathrooms, there are certain steps involved in using the restroom, and I won't describe them. You can just imagine them. And depending on the amount of traffic that you have, people coming into the restroom, you want to tune that to the number of stalls you have, the number of sink bays you have, and so forth. And so this idea of this algorithmic execution is not just for things that are computer science related. It also pertains to any process that can be described as a series of steps, each one of which takes some amount of time. Now, certainly, the number of steps is fixed, and that's part of the design, but the amount of time that each step can take is variable, and moreover, it's stochastic, and you still want to be able to talk about such things because you want to be able to simulate them so that you can use the results of these simulations to make decisions. Because particularly for things like bathroom design or how many folks behind the counter at Subway you want to hire or have working at any given point in time, or how many bathroom stalls or sink stalls in the bathroom you want to install, you don't want to just build it and say, uh-oh, something broke, it didn't work. Let's go ahead and add more bathroom stalls, because you can't do that very easily, for example. And so it's nice to have something computational where you can run a simulation that looks at the probabilities and uses the probabilities associated with the times over this multi-phase execution or multiple step execution, and use those times in simulation to generate events and analyze those results without having to actually say, oops, let me build a new bathroom. Okay, any questions about this? All right, so that's where we left off. And this algorithmic execution, let's continue on, has a name. Each time, as we said, the time between events, so the occurrence of events, we talked about the exponential distribution. And each of these steps in this multi-step execution or multi-stage execution does correspond to an exponential distribution. And so the sequence of steps in the example I gave is 5 steps, and more generally, let's assume the number of steps is going to be described by this variable alpha, right? So you have alpha many steps in a sequence, and each step is governed by an exponential distribution. So here we have alpha, the number of steps, and each step takes exponential, where the exponential distribution is governed by lambda, a rate. So you can imagine if you were going to do this for real, right? You'd analyze a problem, you divide that problem into a number of steps, and then you'd time each step again and again and again and again and again, and you'd come up with a rate, on average rate, for all the steps, and then you'd actually use this distribution to simulate and then ask questions about that simulation. And so this has a name. It's called the gamma distribution. And like other distributions, we see a relationship between the gamma and the exponential, like how we saw a relationship for the geometric between the Bernoulli and the geometric, right? And we saw a relationship between the binomial and the Bernoulli, right? And so here we see a relationship between the gamma. It's just a number, alpha many exponential distributions, one after the other, to define an algorithmic execution. So here we have the gamma distribution, and you note that as x, and that squiggle means is distributed as. That's how you'd pronounce it. So x is distributed as a gamma distribution, and that gamma distribution is governed by 2 parameters: alpha, the number of steps in your algorithmic execution, and lambda, which is the rate parameter associated with the time observation. And so this is a continuous distribution. And the reason why it's a continuous or real value distribution is because we're trafficking in time here. And time is uncountably infinite, and therefore this is a continuous distribution, and we call this probability a density function. Now, in this particular example, the assumption here is that x is going to be greater than 0, because you're not going to talk about 0 time. You're going to have actual non-zero values of time. And what it's measuring is the probability of x, the time, is what the time is going to take to execute this multi-stage execution given a rate lambda and alpha many stages. And so there are a bunch of parts to this here in this density function, f of x. We have lambda exponentiated to the alpha power, and then we have in the numerator, and then in the denominator, we have this gamma of a. Now, it's called a gamma distribution because of this gamma. And gamma is nothing more than a wonky type of factorial, right? If you give gamma function a positive integer a, that's the same, you'd compute it as a minus 1 quantity factorial. If you give the gamma function a real number, and that's not our concern here because alpha is always an integer for this multi-stage execution. There's no such thing as step 1.3, right? That doesn't happen. It's always a whole number, step 1, step 2, step 3, so forth, a positive integer. So while we're only concerned about gamma for positive integers, this a minus 1 factorial, we do have a definition for gamma if you give it a real number. Okay. Any questions about this? So this is our gamma density, and if we wanted to, let me take a step back here, we have the cumulative distribution function of the gamma, and as a density, we can't talk about very easily the probability of a single data point because the law of total probability doesn't permit us to, because there are an uncountably infinite number of times x. And so we can't really simplify the expression for the CDF. And recall the CDF is just the integral from minus infinity to some value t uh, uh, for this density function integrated. And so because this gamma density is 0 from minus infinity to 0, we can get away with this writing 0 plus, and here for the CDF, we only evaluate that integral from 0 to t. And so again, we're using the definite integral, the indefinite integral rather, to compute this definite integral. Okay, any questions about this? All right, so we do know that as a probability, and the proof of this, direct proof, is beyond the scope of what we're going to do in this class. But we do know that this is a probability, and we do know that the law of total probability does apply, right? And so law of total probability says that if you integrate the density function from minus infinity to plus infinity, that's going to equal 1. And because this density function for the gamma distribution is 0 from minus infinity to 0, then we only consider the integral from 0 to positive infinity. So if this is equal to 1, what we can do is use a little bit of algebra, and kind of, well, it looks like a trick, but it's not really a trick. But we use a little bit of algebra to come up with a definition that we're going to use to simplify expressions that'll give us some tools we need to compute the expectation and the variance, which we'll do today for the gamma distribution. So given this identity for the law of total probability, we have the infinite integral from 0 to infinity of the density function that's equal to 1, because all of the probabilities added up together, and in this case we're using integration because it's a continuous distribution, it's a density function, we're going to use the integral. So we have that expression, and we're going to replace for f of x our definition of the density function for the gamma distribution. So we write the integral from 0 to positive infinity. This monitor gives off a lot of heat, and if you ever work at boards and stuff, you notice little weird things like that. So every time I walk over here, I feel great because it's warm, and over here there's like a cold spot. So anyways, I digress. So we have that infinite integral, and we replace f of x with the density function for the gamma distribution. And so we have our gamma to the alpha upon gamma of alpha, and then we have our x to the alpha minus 1, e to the minus lambda x. Okay, so now if we look at this expression under the integral, now recall what the integral is, that's the Riemannian sum. We're taking this dx, our tiny little sliver of x, and we're using that to add up the area of these tiny little sliver rectangles. And so the capture variable under this integration is anything that involves x. So we have x here, x to the alpha minus 1, e to the minus lambda x. But this alpha gamma to the alpha over gamma, I'm sorry, lambda to the alpha over gamma of alpha, that does not involve x anywhere. So for all intents and purposes, they look like constants under this integration, so we can pull it out front from under the integration. So we have that, and we have this leading coefficient, lambda to the alpha over gamma of alpha, and then we have what remains, our infinite integral from 0 to infinity of x exponentiated to the alpha minus 1 and e to the minus lambda x. Okay, dx equals 1, because it's still the law of total probability. So now we notice here we have this expression on the left of equality, and we have 1 on the right of equality. So if I multiply both sides of equality by gamma of alpha, well, this gamma of alpha here cancels out. And if I divide both sides of equality by this lambda to the alpha, well, this lambda to the alpha cancels out on the left-hand side. And so what I'm left with is the infinite integral of x exponentiated to the alpha minus 1, e to the minus lambda x. And on the right-hand side of equality, what used to be 1, I have gamma of alpha over lambda to the alpha power. Okay. Any questions about that? Does that make sense? So this is a little bit of algebra, and I started with the law of total probability, and I used the definition of equality, and I multiplied after factoring out that leading coefficient, and I get this expression. And so one observation to note here is if I look at this pattern, it says every time I write this infinite integral, right, I can replace it with this expression. And the relationship between this replacement and the infinite integral is here I see alpha. Here I see alpha minus 1. Here I see alpha. And so that means when I make a replacement, every time I see this infinite integral, if I make this replacement, I have to make sure that the alpha terms in this right-hand side of equality are one more than the alpha term on the left-hand side of equality. Here we have alpha minus 1. If you add 1 to alpha minus 1, that's alpha. That's gamma of alpha. It's over lambda of alpha. Okay? Make sense? Any questions? All right, so let's work with that. And now we're going to look at the expectation. So for this expectation, what are we going to do? The expectation is just the probabilistic average. And let me grab my marker. And the probabilistic average says if I have a density function, the expectation is the integral from minus infinity to plus infinity of x times the density of x dx. Okay. So we also know, of course, that this gamma density is 0 everywhere from minus infinity to 0, right? So I can write minus infinity to 0 of x, f of x dx plus integral 0 to positive infinity x, f of x dx. So this part goes to 0 because my gamma density is 0 everywhere from minus infinity to 0. And all I'm left with is this expression. So I take that infinite integral and I take x and I multiply by f of x. F of x is nothing more than this density here. So I have this leading coefficient, gamma to the lambda to the alpha power over gamma of alpha. That should be alpha, not a. I'm sorry. No. That's, yeah, alpha. And then I have x to the alpha minus 1, e to the minus lambda x. Okay, so now I compute my expectation, right? So here's my x, and here's my f of x. So I replace f of x with the density for the gamma function. And in one step, here's my lambda to the alpha, gamma of alpha. Here's my x to the alpha minus 1, e to the minus lambda x dx. So I multiply that by x. And in the same step, I recognize the fact that this leading coefficient does not involve a, so I bring it out from underneath my expectation, our integral. Okay, so now I take that integral and I have an x times x to the alpha minus 1 power e to the minus lambda x. Well, I have the same x here, and so this x is the same as x to the 1 power, and so I add my exponents here. So now if I do that reduction, I have the infinite integral from 0 to infinity. I have my leading coefficient here involving lambda to the alpha and the gamma function in the denominator. I have x to the alpha power e to the minus lambda x dx. Okay, any questions about this? Does this make sense? So now I take this expression and I'm going to use this identity I had before from when I did the law of total probability. And it says that I can replace this infinite integral by this expression, gamma of alpha over gamma over lambda to the alpha power. I can do that replacement. I just have to make sure the value of alpha is one more on the right-hand side than it is on the left-hand side. So here I have x to some power. I have e to the minus lambda x dx. It's the infinite integral. It's the right form. If I do that replacement using this identity, well, 1 more than alpha is alpha plus 1. So I'm going to have a gamma of alpha plus 1. And then 1 more than alpha is alpha plus 1. So I'm going to have a lambda to the alpha plus 1 power. Okay. So I do that, and I get the following expression. I just do a wholesale replacement of this infinite integral using this identity that I arrived upon from the law of total probability. So that leaves me with this expression. I have a gamma of alpha here in the denominator, a gamma of alpha plus 1 in the numerator. I have a lambda to the alpha in the numerator. I have a lambda to the alpha plus 1 in the denominator. So now, using the definition of what my gamma function is, let's recall that if I said gamma of alpha, that's the same as alpha minus 1 quantity factorial. So that means if I said gamma of alpha plus 1, that would be the same as alpha plus 1 minus 1 quantity factorial. Well, alpha plus 1 minus 1 is the same is alpha factorial. Okay, so using that fact here, alpha factorial, by definition of factorial, is alpha times alpha minus 1 quantity factorial, because alpha factorial is just alpha times alpha minus 1 times alpha minus 2 dot 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 times 2 times 1. So that leaves me this gamma of alpha plus 1. I can rewrite that as alpha times alpha minus 1 quantity factorial, and that's that term here, this gamma of alpha plus 1. Now, of course, if I collect the denominators, because I'm multiplying these, I can reverse the two denominators just to have like kind below like kind here. And so that's this gamma that used to be this gamma of alpha plus 1, right? And then here I have this gamma of alpha. Gamma of alpha is just alpha minus 1 quantity factorial. So that is my gamma of alpha. And then, of course, I have this lambda to the alpha power, and I have in the denominator lambda to the alpha plus 1. Lambda to the alpha plus 1 is just the same as lambda to the alpha times lambda. Okay, so using those reductions, I get the following expression, and I have lambda to the alpha in the numerator, lambda to the alpha in the denominator. This goes to 1. That leaves me with 1 over alpha, 1 over lambda, and then here I have alpha minus 1 factorial in the numerator, alpha minus 1 factorial in the denominator. Those cancel, and so I'm left with 1 over lambda times alpha over 1, which is just the same as alpha over lambda. Okay, does that make sense? Any questions about this? So that is the expectation of a gamma random variable, alpha upon lambda. Okay, so this is our expectation. And we're going to use the variance equation. When solving the variance, we're going to use the variance equation, which we came upon by working through the definition of variance. And that variance equation says that if I want the variance of a variable, that's the expectation of that variable squared minus the expectation of that variable quantity squared. Now, we just got done computing what E of x is, and that's alpha upon lambda. And so if we were computing the variance using the variance equation, we're sort of halfway there. Right, so the variance of our gamma random variable x is equal to E of x squared minus E of x quantity squared. Now, we just got done showing that E of x, our expectation of the gamma random variable, is alpha upon lambda. So if I square that, that's equal to alpha squared over lambda squared. So we're kind of halfway there. What remains now is to calculate this E of x squared. All right. Any questions? All right. So if we do this E of x squared, well, E of x squared, we have our x squared, and we multiply by the density function of the gamma function. And of course, that leading coefficient we can bring outside of our integration. So I have this lambda to the alpha power upon gamma of alpha. I have my infinite integral dx, and then I have my x squared times the rest of the density function, x to the alpha minus 1, e to the minus lambda x. So now I combine my x's because I have x squared and an x to the alpha minus 1 power. So those exponents add. So 2 plus alpha minus 1 is alpha plus 1. Okay, and so I get the following expression. Now my exponent on the x is alpha plus 1. Okay, any questions about this? So then I make use of this identity once again here that I came upon from the law of total probability. And again, it says whatever my alpha exponent is, I add 1 to it, and that's my version of alpha on the right hand side of equality. And so here, this expression is x to the alpha plus 1. So I take alpha plus 1 and I add 1, that's alpha plus 2. So that's going to be gamma of alpha plus 2 over lambda to the alpha plus 2 power. So I make that substitution. I do that, I still keep my leading coefficient, and now I have the following expression. I have lambda to the alpha power in the numerator. I have lambda to the alpha plus 2 power in the denominator. And because I'm multiplying those two fractions together, I can reverse the denominators. It's not addition, it's multiplication. So I say lambda to the alpha over lambda to the alpha plus 2 multiplied by, and in the numerator for the gamma functions, I have gamma of alpha plus 2 in the numerator, and I have gamma of alpha in the denominator. Now again, by definition of the gamma function, if I have gamma of alpha plus 2, that's the same as alpha plus 2 minus 1 factorial, which is the same as alpha plus 1 factorial. Now, by definition of factorial, that's just alpha plus 1 times alpha minus 1 quantity factorial. Now, if I continue that on, that'd be times alpha minus 2, times alpha minus 3, and so forth, up to times 2 and times 1. So I do that, and I look at this expression. I have in the numerator gamma of alpha plus 2. So I replace that gamma of alpha plus 2 with alpha plus 1 quantity factorial. And then by definition of the gamma function for the denominator, that's just alpha minus 1 quantity factorial. Alpha minus 1 quantity factorial. And so now I peel off terms for the numerator in that factorial, and that's alpha plus 1 times alpha. So that's alpha plus 1 times alpha minus 1 quantity factorial. So, okay, I can rewrite the denominator for this lambda term. And for this lambda term, I write lambda squared times lambda to the alpha power, because lambda to the alpha plus 2 power is just the product of lambda squared and lambda to the alpha. So now I cancel. I have alpha minus 1 in the numerator, and in the denominator, that goes to 1. That leaves the numerator as alpha plus 1 quantity times alpha. And then I have, on the other term for the lambda term, I have lambda to the alpha in the numerator and denominator. That goes to 1. I'm left with 1 over lambda squared in the denominator. So with that, I have, oh, okay, I thought it was someone in the hallway. Okay, that's weird. Alpha plus 1 times alpha in the numerator, and I have lambda squared in the denominator. Okay, so that's the expectation of x squared. Now remember, we were subtracting from that e of x quantity squared, and we just said e of x quantity squared is alpha over lambda quantity squared. So that gives me alpha plus 1 times alpha over lambda squared minus this e of x quantity squared. That would be alpha squared over lambda squared. So both denominators are the same. Excuse me, it just ran out of ran out of moisture in my throat. Excuse me. So the denominators are the same, so I can just combine the numerators. So that is, I can carry out this multiplication. I can distribute that multiplication over the sum. So that's alpha squared plus alpha, right? I get a minus alpha squared from the second term, common denominator lambda squared. The two alpha squares cancel, plus and minus. I'm left with alpha over lambda squared, okay? Oh. Thank you. Oh, my. Thank you. Everything just sort of explodes. Thank you. One of those days. I'm already thinking of Thanksgiving holiday and all the catch-up work I have to do. Thank you. There we go. All right. So we're left with alpha over lambda squared. And that's the expression for our variance for the gamma random variable. Now, of course, it's funny, you go into a shop that's doing some sort of analysis of business case, and, it's, oh, well, let me model this for you and run some simulations. All you're doing is analyzing the scenario, coming up with a bunch of steps, looking at timings for the steps, determining what alpha is, what your rate lambda is. You run something like MATLAB or Python. You run some simulations, just like how you're doing binomial simulation for the example for the was it burritos? Yes, for burritos. And now you have a model that will tell you roughly how much you should spend or how long something's going to take, right? And so you'll be viewed very, very favorably and say, oh, wow, you're going to become our modeling person now. Okay, so this is our variance, alpha upon gamma, lambda squared. I keep calling lambda gamma. I don't know why. I just have gamma on the brain for some reason. But nonetheless, alpha over lambda squared. Okay. Any questions about this? So whenever you want to compute the variance, you start out with the expectation, you use the variance equation, and then you solve for E of x quantity squared, and then you subtract. Okay. All right, so that's our gamma distribution. And let's just introduce the normal distribution, and we will stop after right before, I think, probably mean of the normal distribution. Okay, so the normal distribution is a very important distribution in probability and statistics for two reasons. For one, because the normal distribution is a very good model for so-called inertial systems, and I'll get to what I mean by that in a slide or two, but also because of something called the central limit theorem. The central limit theorem, which we'll talk about after the module, probably on Tuesday after Thanksgiving. The central limit theorem allows you to take any random variable, regardless of its distribution, compute a transformation on it. And when you compute that transformation, if you do it in the suitable way, then the distribution for that will no longer be the same. It'll become a normal distribution. And you might be wondering, why do I want to transform something to a normal distribution? Suppose you want to compare two things. Let's say you want to compare a geometric distribution, all right, the number of failures until you get a success, with a Poisson distribution, the number of events or customers that arrive in time. Now, of course, those two things, it's an apples to oranges comparison. They're not the same. And if you wanted to say which one is more dispersed, or under certain conditions, which one is more favorable, for example, it's really hard to make that comparison because the two are just different. They traffic in different quantities and the distributions are just different. Now, if you can cast them both as equivalent normal distributions, now you can make a fair comparison between the two. And the central limit theorem affords you the ability to be able to do that. And we'll end the semester with central limit theorem and talk about modeling a week from Thursday and have some examples. And the homework with the binomial simulation is just one type of modeling you can do. Okay, so the reading has not changed. I've added on a couple more pages to get you through to the central limit theorem. Please make sure you are getting the reading done. Now, when I say 5th of December, don't work over Thanksgiving. I really, for personal reasons, going back to when I was an undergrad and we had homework over Thanksgiving break. And I remember saying, damn it, if I become a professor, I will not assign homework over Thanksgiving break. So guess what? I'm not assigning homework over Thanksgiving break. So what I mean is that, start it on Monday, right? But don't do anything. And that's how I've tuned the courses, both my courses, all my courses, undergrad and grad, so you're not doing work over break. I expect you to enjoy it with your families, friends, and loved ones. All right. Okay. So that being said, when we talk about certain quantities like pressure, heat, force, audio amplitude, light, oftentimes things are governed by inertial systems. And by inertial, I mean that as something changes over time, its future value has a lot to do with its current value. It doesn't just mysteriously go from one value to another that's very different. It's always one value plus or minus some little delta. And that's the definition of an inertial system. Take, for example, motion, right? And in a desperate effort to make this interesting, found an interesting video. And this video, you take like slime or Play-Doh or something kind of gooey, and you put it on a speaker cone, cover it with saran wrap so you don't mess up the speaker cone, and just start playing some music. And all the vibrations from the constituent frequencies of the sound as the speaker cone oscillates to produce sound, you're going to see it sort of arise in this Play-Doh. It works with Jello. It works with better with something like putty, Play-Doh, or if you ever made Play-Doh, because I have a 7-year-old, I have a lot of experience making Play-Doh. You get flour, you mix it with water and salt and stuff, and then it kind of gets gooey, and you cook it down, and eventually it's kind of doughy, and you can use it as Play-Doh. So you have a bunch of that, you put on a speaker cone, and it's really kind of, to me, it's kind of relaxing. It's eerily kind of interesting to just sit and watch it, and it kind of dances to the beat of the music in a sense, which is kind of weird, but kind of funny. And it's even more cool if you have different things with different colors, but the colors haven't mixed, you'll see it start to mix the colors. It's pretty interesting. And so, of course, you'll notice when it moves around, its future location, even though it's moving around randomly, right? Seemingly, not randomly, stochastically, its future position, it's somewhere nearby its old position, plus or minus some delta, right? And so, how do you describe stuff like that? Well, let me tell you. I'm glad you asked. Um, this inertial quantity is a specific type of system, and it's a system you observe, like position, velocity, and so forth. And it's governed by this quality or property that the immediate future state is determined by the current state. So let's say, position, someone's walking or running or what have you, and you measure his or her position now, and then like maybe 100 milliseconds from now. Well, 100 milliseconds from now, you can assume that where they are 100 milliseconds later is somewhere nearby where they currently are, right? And so this quantity is called inertial. The future state is determined by the current state plus some little change. You don't just simply change the arbitrary value. So you can imagine if you're trying to measure someone's position, right now your friend was like in one location, and then a millisecond later they were all the way down the hallway, right? That'd be like weird. You think, is this person like some sort of shapeshifter or something like that? And so quantities that are inertial, could be temperature, pressure, position, velocity, are well described by a so-called normal distribution. Now, the normal distribution sometimes in the literature is called the Gaussian distribution, and this is the density of it. It's 1 over square root of 2 pi sigma squared times e to the minus 1 half x, e to the minus x minus mu. And so this is the characteristic bell curve shape, right? And these parameters here that govern this bell curve are known as the mean mu and the variance sigma squared. Now, in the literature and statistics, especially as you go to graduate level, but as you talk about more generally distributions, you describe distributions by how these so-called parameters affect the distribution. And for the normal distribution, these are called location scale parameters. Now, the mean or center of mass of this distribution defines the center location of all of the data points governed by this distribution. And so on the horizontal axis, we have the value. On the vertical axis, we have the probability. And so the mean mu, when you compute the expectation, that's exactly the center value, right? Everything is bigger than that and less than that is half of the probability, right? That's what the definition of the mean is. And so as you change the mean of a distribution, you basically take this distribution and you shift it to the left or shift it to the right. You're changing its location. Now, scale corresponds to how dispersed or how spread out this probability mass is, plus and minus around the mean. If our variance sigma squared is large, well, the standard deviation is the square root of variance, and this is a standard deviation. That means this thing is more flattened. It's smaller, shorter, less probability mass, but that probability mass is kind of spread out evenly. So imagine, the only example I can think of, imagine you have like, a certain amount of peanut butter, 1 unit of peanut butter. It could be 1 gram, 1 cup. Now, if you have a small variance, imagine there's no peanut butter over here, like on a board or something. For some weird reason, want to spread peanut butter on a board. But imagine it's one big glop right here, right? You don't have it very spread out, right? That's what a small variance is, and therefore small standard deviation means. Now, if you were to take that big glop of peanut butter and you mush it down and spread it out as far as you can, that would be akin to increasing the variance or large standard deviation. And this scale refers to how far out your probability mass is spread, right? So you can have a larger spread, and what that corresponds to is a higher variance and higher standard deviation. And from a data standpoint, it means you're going to have many more different values as observations. Now, take, for example, something like a security, like a stock. If you have a high variance stock, let's say for the trading day, I think the trading window opens up at 9 or 9:30 and closes at 4:30, I think 9 to 4:30. If you have a high variance stock, that means the value of the stock is going to jump up and down a lot. You can have a lot of different values it's going to take on. Take, for example, the temperature today. 5 o'clock this morning, it was 34 degrees. This afternoon, it's going to hit 69 degrees. That's a high variability because in going from 32 degrees to 69 degrees, you went through a lot of different values that you observed. That's a high variance. And if you were to represent the distribution of temperatures today, and plot the probability of each temperature at which it occurred, and as a distribution that counts proportionally, you'd get a bell curve shape, right? And that would be more spread out. But if you took a day where the temperature, say, was at 42 and it only got as high as 45, you're going to have something that's more like that gloppy peanut butter I alluded to before. Okay, does that make sense? And so when you talk about distributions, oftentimes macroscopically, you talk about how the parameters affect the shape of the distribution, the location, and or the scale, right? Now, some distributions, like the Poisson distribution, it's only going to affect the shape, right? It's going to take that Poisson and it's going to kind of make it more mushed to the left or mushed to the right. So when you talk about a model, they'll say, oh, the normal distribution is a location scale model, right? You can either shift the location or make it more spread out. But the Poisson is just a shape model, meaning that you can only affect the shape, make it more lopsided to one side or the other, depending on the value of lambda, the rate. Okay? All right. Any questions about this? Does that make sense? So this normal distribution is particularly important because a lot of quantities that you measure are well defined by a normal distribution. Okay, so the other interesting part about this normal distribution pertains to the relationship between the area under the curve, the mean, i.e. the center, the location, and the standard deviation, the amount of dispersion. So in this particular graph, I have the mean, and in this case, this normal distribution is centered so that the mean is right at origin at 0. And you'll notice here certain tick marks. It says 1 sigma, 1 times the standard deviation, 2 times the standard deviation, minus 1 times the standard deviation, minus 2 times the standard deviation. And the interesting part about this is that if you were to do an integral between the bounds of certain distances away from the mean, and that distance is measured in terms of multiples of standard deviations, you're going to get a certain percentage of the total probability. So if you go minus 1 standard deviation and plus 1 standard deviation, and were to take the area under the curve of that region, you're going to get about 68% of the probability, right? If you go plus or minus 2 standard deviations from minus 2 sigma plus 2 sigma, and you integrate everything, you're going to go about 98, 99% of the probability mass, right? And the reason why that matters is something called hypothesis testing. Now, what you do when you're trying to determine whether something is typical or something's an oddball, a measurement, oftentimes when you have a system, you want to reject the oddball measurements. Take, for example, spam filters, right? You've all probably used the spam filter in like Gmail or Yahoo, if anyone still uses Yahoo Mail. You get some spam email, and it automatically says, this is spam, and it puts it in your spam folder. And then you look in your spam folder and say, wait a minute, that's not really spam. You correct it, and it puts it back into the normal inbox. Okay, so how is this spam filter working? What it's doing is it's calculating distributions over words that occur in real emails. And then when you get a new email, what does it do? It says, I have these words. Let me test to see if those word values are typical of what an email is. And another way of measuring typical is to say, does it correspond to those values that represent 95% of your total probability, right? That's what it means to be typical statistically. So what does it do? And it just so happens one plus or minus 1.96 standard deviations, if you were to integrate, that would be 95% of the probability mass. So what is it doing? It's testing to see if you are part of this 95% membership to distribution of values that are typical, right? And that's what typical means. And so what your spam filter is doing, Google and Yahoo, they're building big distributions over words that are from typical emails, both from your emails as well as emails across millions of other accounts. And then when a new email comes in, it tests it against these distributions to see if it's in the 95% probability mass region. If it's outside, it's atypical, tag you as spam, put it in your spam box. Now, of course, if it makes a mistake, what do? You correct it. You say, hey, wait a minute. This is not atypical. It's a weird email, but it's a legitimate email. Bless you. So what it does, when you mark it as legitimate email, and before it puts it into your inbox, it'll take that word, that new email, It'll add it to all the other emails that it used to create the distribution, and it'll recalculate the distribution. So that plus or minus 1.96, the standard deviation, now changes a little bit because you've added to the data. And that's exactly what these spam filters do. If you are trying to filter out noise in a signal, you're doing hypothesis testing, outlier detection. And I'll show you an example of that probably Tuesday. I had a capstone student, Emlyn Foreign. She did something called Physical Therapist in a Box. She used IMU motion trackers to determine if someone is walking normally, normal gait, or abnormal gait. And it was literally hypothesis testing using normal distributions from data measured for the joint motions for what normal walking is. Okay? So it's a really powerful mechanism, this normal distribution, and you can use the relationship between the center and the scale parameter to do this so-called hypothesis testing as a way of determining whether or not a new measurement is typical of the old measurements. And how you connote typical is it in the 95% probability mass region for the distribution that you created from a bunch of data? Is it typical, or does it belong to, is it an oddball with respect to that existing data? Okay? Any questions about this? Does that make sense? So while we're just scratching the surface, we needed to build up these tools over the course of the semester, and we'll spend a tiny bit of time with the modeling, and then certainly next semester in data analytics, we'll use it with statistics to do all sorts of interesting things. But you can't get to the modeling until you understand the distributions and the relationships between them and a little bit of simulation. Okay, so let me do a time check. 12:50. So of course, as a density function, it adheres to the law of total probability, and that means that if we take the integral between plus and minus infinity, that equals 1. So what does that mean? That says if you take the integral plus and minus infinity, now for the case of the normal distribution, it is non-zero plus and minus infinity. Now certainly, depending on the standard deviation, it'll go closer to 0 faster or closer to 0 more slowly, but you still take the integral between plus and minus infinity of your density function, dx. So that's the law of total probability. It still follows for every distribution, regardless of whether you're a continuous distribution or discrete distribution. So let's look at the expectation. We have the expectation of normal random variable is mu, and the variance is sigma squared. Okay, so let's take a look at this law of total probability. We'll show that, and we'll end with that and pick back up on Tuesday with the mean and the variance. And so law of total probability says we take the infinite integral over all possible values, minus infinity to plus infinity, of the density function dx. So it's our Riemannian sum. We substitute for the density function for the normal or Gaussian random variable. That's 1 over square root radical 2 pi sigma e to the minus 1/2, I had a typo before, e to the minus 1/2 sigma squared x minus mu quantity squared dx, right? So this is like, oh crap, that's yeah, there's a typo there. I'll correct that. This is missing. Let me just write it on the board. F of x is equal to 1 over radical 2 pi sigma squared e to the minus 1 over 2 sigma squared x minus mu quantity squared. Okay, I don't know why there's a typo. That up top is wrong. This is correct down below. Okay, so we take that infinite integral between plus and minus infinity, and we start out this radical 2 pi sigma squared, that's a constant underneath the integration, so we can bring that out front for this integral. And so now we need this infinite integral for this e to the minus 1/2, 1 upon 2 sigma squared times x minus mu quantity squared dx. And so we're going to do a u substitution and compute the Jacobian for this. So we're going to let u equal this entire complex exponent here, x minus mu quantity squared over 2 sigma squared. Gosh, I am just completely, this should be sigma squared. You don't see it when you're making the slide, but you see it when you're showing it. All right. Anyways, that should be over radical 2 sigma squared. No, that's not right. Is that right? What did I do? What did I do? For u is equal to. Okay, no, that's right. That's right. All right. All right. Because I want to have 2, that's the squaring of that radical 2. Okay, jumping ahead of myself. Okay, so that's correct. So we're going to do a substitution, and we treat this term here. You notice here the numerator is squared, and the denominator, we have a sigma squared. It'll work out if we treat this 2 as if it's something squared, right? Because we're going to need that to cancel out this term, right? So here, when we do the Jacobian, we're going to let u equal x minus mu over radical 2 sigma. And the reason for that is we want to have something that says u squared, right? And the only way we can have something squared with the substitution is by taking the square root of this constant here, right? So that's why we do that. I jumped ahead of myself. All right, so there's our substitution for u. And okay, that means du is equal to 1 over radical 2 sigma dx. And we do a little algebra, and we're left with radical 2 sigma du is equal to dx. So that means with this u substitution, if I have a change dx, and I want to change that to du, I have a commensurate scalar factor of radical 2 sigma that I have to incorporate. So this is your standard Jacobian, and it allows us to change variable for our integration. Any questions about this? Does that make sense? Okay, so let's continue. So we do that substitution, and now I have radical 2 sigma, right? That's the scalar factor when as a result of the Jacobian. I change dx to du, and now instead of e to this complex exponent, I have e to the u squared. And the reason for saying that substitution was radical 2 was so that I could call it e to the u squared, right? It wouldn't work out with that 2 if I didn't make it radical 2. Okay, so now, any questions about this step? No? All right. So now, I take this constant, this radical 2 sigma, that's a constant, does not involve u, so I can move that out of the integration. And when I move that out of the integration, I have radical 2 sigma in the numerator, and I have radical 2 pi sigma squared in the denominator, okay? All right, so this e to the minus u, that's just e to the minus u squared power du, that infinite integral. That's something called the Gaussian integral, right? So I have a YouTube video linked. It's beyond the scope, the derivation of this class, but you'll just have to take it on, take my word for it. If you don't believe me, watch the video. They do the derivation. That infinite integral of e to the minus u squared is equal to pi, radical pi. There's a beautiful relationship between e to the x, sine, cosine, and pi that'll just blow your mind. Maybe one day I'll do a department seminar on it, right? Just this amazing that kind of ties together all this crazy stuff. Okay. Anyway, so this infinite integral is called the Gaussian integral, and that's why this is called the Gaussian distribution, right? Gauss is someone's last name, this mathematician who did this. And there's the YouTube video if you don't believe me, and I hope you don't believe me, and actually take me up on it and watch it. So anyways, I can replace this integral through the Gaussian integral with the substitution of radical pi. And so let me do that. So now I have 1 over radical 2 pi sigma squared. I have a radical 2, I have a radical pi, and I have a sigma. Oh, wait a minute. Everything cancels, right? So I have radical 2 here, I have radical pi, and radical of sigma squared is just sigma, right? So I'm left with just 1, okay? And so this was law of total probability. I take that integral of the density function for the Gaussian distribution between minus and plus infinity, and I get exactly 1. So lo and behold, it is indeed a probability. Okay. Any questions about this? No? Yes? Okay, so we will save for Tuesday the derivation of the mean and the variance. It's just more algebra and a little bit of calculus. And I will end there.